Okay, that's fine. All right, what are we working on tonight?
So here's something I didn't understand at all.
Okay.
So to express each of the following functions as an algebraic expression involving no trig function.
Okay.
So the first one is sine or cosine of inverse sine 2x.
Hold on. So it's cosine of inverse sine of 2x, like that?
Yeah.
Okay. Is that all they give you?
Yep.
All right. If we draw a triangle, and label that theta, if the inverse sine is 2x, then that's 2x, and that's 1. In other words, the sine of theta would be 2x over 1. So the inverse sine of 2x over 1 is equal to theta. Okay. Now let's dimension the rest of that triangle. If those are two of the dimensions, what's the third one?
Okay.
Use the Pythagorean theorem.
So do the square root of 1 squared minus 2x squared.
That's the dimension of that third side. Now, what's the cosine? Remember, this is theta. So what's the cosine of theta?
So would it just be cosine equals that, or would we have to?
Well, looking at that triangle, what's the cosine of theta?
Oh,
Adjacent over hypotenuse.
Yeah, so it would just be that over 1.
There's your answer. There's no trig functions in that.
Okay.
It's a polynomial. That's pretty much the way we're going to do all of these, is by drawing a triangle, dimensioning two sides, figuring out the third, and so forth and so on.
Okay.
Okay.
The next one is secant squared inverse tangent x.
Inverse what?
Tangent.
Dimension this for me.
So opposite will be x, adjacent 1.
square root. Whenever you're solving right triangles, the answer always starts out square root. Now sometimes it's the square root of 25, which is a whole number, but always remember it's square root of the sum of those squares. So x squared plus 1. Okay, in other words, this is theta. Theta is equal to the inverse tan of x. Therefore, this triangle fits this picture. Now, according to this triangle, what is the secant squared of theta? What's the secant of theta?
So adjacent or hypotenuse over adjacent. So
Correct. So what's the secant squared of theta?
oh, would it just be secant squared equals x squared plus 1?
There it is. In other words, that's equal to x squared plus 1.
Okay.
These are fairly difficult. I don't run across this degree of difficulty that often. It's not really much different than saying if the sine of theta equals 3/7, what does the tangent of theta equal? Well, if we were to solve this, we would draw our triangle, we would label theta. If the sine of theta is 3/7, that has to be 3, that has to be 7. That makes this side square root of 40. So tangent of theta would be 3 over square root of 40, and then you'd have to rationalize that and simplify it. But it's basically doing that. That's what these two problems you've given me are doing, only instead of numbers, they're giving you variables, kind of. And then you just have to dimension your triangle with variables instead of numbers.
The next one is sine of inverse cosine root x.
Remember, that's always theta. Whenever you take the inverse trig function of something, you're going to get an angle. Okay? So, dimension this.
So
Adjacent would be
the root of x. Opposite or hypotenuse be 1. And that'll be the square root of 1 minus root. That would just be x.
Okay. So now what is the sine of theta?
That'll be root 1 minus x over.
And we could substitute numbers to prove all of this. But we don't really need to. In other words, this would be an easier problem if they said the inverse cosine of root 3 over 2. Okay? Let's talk about this problem right here. Well, that allows me to draw the triangle and label it root 3, 2, which makes that 1. And now I'm taking the sine of theta, which is 1/2. So this whole thing would be 1/2. So by substituting variables instead of numbers, in other words, by calling this square root of x or even x or x plus 1, whatever, it just forces us to label that triangle differently. What else, Daniel?
That's negative cosecant squared of the inverse cotangent x.
Where's the x and the 1 go?
So adjacent will be x, and opposite will be 1.
Which makes the hypotenuse
Root of x plus 1.
okay. What is the negative cosecant of theta?
So
Just for the moment, what's negative cosecant instead of negative cosecant squared? In other words, it's important to realize that this square here does not apply to the negative sign. It was not like that. So we're going to square the cosecant and then put a negative sign in front of it. So first of all, what's the cosecant of theta? This whole thing in the parentheses is theta. So cosecant of theta would be what?
so that'll be the root of x squared plus 1 over 1.
Okay. What's cosecant squared of theta?
That'll just be x squared plus 1.
And what's negative cosecant squared of theta?
Negative x squared minus 1.
Yeah, you got to distribute it to both terms. In other words, this whole part of it was x squared plus 1. Distributing the negative sign to everything that's inside those outside parentheses makes it minus x squared minus 1.
Okay.
Do you have answers on any of these?
The odds have answered in the past, I believe.
You know, it's been so long since I've done these kind of problems that I wouldn't mind you checking one of them to make sure we got it right.
Well, this one's actually, like, they're all under 56, so I don't have the answer to that.
Okay. I'm 95% I'm sure that we've done it right here. It's just it's been a while since I've done this complicated one. But yeah, I don't know what other way to do it. It's got to be the right way we're going about doing it.
And the last one of those is tangent of inverse secant x squared.
For my dimensions. Hypotenuse is what? And which side is 1?
Adjacent.
Making this side
Root of x squared minus 1. Oh.
Right?
Yeah.
Okay. So tangent of theta what's that?
Okay.
I think that's, I didn't make a mistake here, did I? Let's see. Secant of theta would be x squared over 1, the reciprocal of cosine. And that leaves this side as the square root of this squared minus this squared. That's x to the 4th minus 1. Yeah. Okay, what other kinds of problems do you have? These should be good. I love trig. I find it very challenging. I like it when we get challenged.
Alright, so here's a word problem.
Okay.
So the first one is the angle of compression from the top of the Smoketown Lighthouse 120 feet above the surface of the water buoy is 10 degrees.
10 degrees?
Yeah. Well, in the picture they have the angle like above there, like it.
This is the 10 degree angle. Okay.
Yeah.
So this one actually would be 8. Okay. Make it like that. This is the water.
Yeah.
Okay.
And it wants to know how far, so it's just that bottom line pretty much.
This distance here?
Yeah.
What's this angle right here?
So that'll be 90 minus, so just 10 degrees?
That's 10 degrees. In other words, this dotted line is parallel to the water line. So we have two parallel lines and a transversal. This angle is equal to this angle. So now, give me a trig function that solves for x. And always start these with the trig function. In other words,
I would not use the law of sines for something like this, so.
We can say that the tangent of 10 degrees, which is a number you can get out of your calculator, is equal to 120 over x. That's all. We don't need to use the law of sines to solve this triangle.
Okay.
We could, because we do know that that's 80 degrees. And we know that the sine of 10 divided by 120 would be the same as the sine of 80 divided by x. But when you're dealing with right triangles, you don't tend to use the law of sines. You don't really use the law of sines unless you have to. This is very straightforward triangle to solve because it's a right triangle. If it's not a right triangle, that's when you have to use the law of sines. In other words, if I say solve this triangle here, and I say this is 70, that's 60, making this 50, and this side's 10, solve for x, notice I can no longer use my standard trig functions to solve for x. In other words, I can't say that the tangent of 50 degrees is 10 divided by x. That's only true in right triangles, that it's the opposite over the adjacent. When you're looking at triangles that aren't right triangles, you have to use the law of sines to solve this. In other words, I could say that x over the sine of 70 equals 10 over the sine of 50. Well, that's a number, that's a number, that's a number. X is very easily solved for. The only way I can solve for it is using the law of sines. Maybe could use the law of cosines, but if you're going to use the easiest thing, you're going to use the law of sines there. But when you're dealing with right triangles, you never really have to use the law of sines. You can just use the standard trig functions. As long as you have one angle and one side like this. In other words, this situation here, one trig function, as long as I use the tangent function, I'm fine. I wouldn't want to use the sine function because then the sine of 10 degrees is 120 over the hypotenuse, and I'm not trying to solve for the hypotenuse. So you got to be able to pick the trig function. Now this makes x equal to 120 divided by the tan of 10 degrees. So there's your answer, whatever the tan of 10 degrees is. If you want me to come up with answers, I can pull up my virtual calculator, my TI-84, and come up with answers here to make sure that you're getting them on your end also? Okay. Once we get it to this step, you're cool?
Yeah.
All right. That's going to be a pretty far distance, incidentally. In other words, x is going to be significantly greater than 120. If this were a 45-degree angle, x would be 120. The fact that it's much, much smaller means this distance has to be much, much larger. So that's probably going to come out to be 400 or 500 feet. 120 divided by the tan of 10 degrees. What else?
Another word problem there. So
Okay.
a wire stretches from the top of a vertical pole to a point on the level ground 16 feet from the base of the pole. If the wire makes an angle of 62 degrees with the ground, find the height of the pole and the length of the wire.
Accurate picture?
They don't have a picture for this.
The y is the vertical pole. The wire is z. And the base of the wire, they said, was 16 feet from the base of the vertical pole, right?
Yeah.
Okay. So let's solve for y. What trig function will relate y to a number? In other words, it's not going to do us any good if we say the sine of 62 degrees equals y over z. That leaves us with two variables. We wouldn't be able to solve for either one of them. So we want to make sure we use a trig function that relates one of the known number that we have, 16, with y, or 16 with z. We'll do two separate problems. Let's solve for y first. What trig function relates y and 16?
Tangent.
So we got the tangent of 62 degrees equals y over 16, so y equals 16 times tangent of 62 degrees.
Okay.
And then what relates z to 16?
Cosine.
So cosine of 62 degrees would be equal to 16 over z. Slightly more difficult to solve because my unknown is in the denominator, so I have to kind of cross multiply. Got to multiply both sides by z and then divide both sides by cosine of 62. there's Z, and there's Y. And you could also have gotten Z. Once you figure out Y, you can get Z using the Pythagorean theorem if you like, but I presume they would rather you use trig functions.
Yeah.
I mean, given the subject matter you're covering. I can think of a little harder word problem than these. But go ahead. If we run out of time at the end, I'll give you my harder word problem.
All right. Yeah, why don't we do the harder one, and then we can do these, because these are pretty easy.
Yeah, these are all basically one trig function.
Yeah.
That's a mountain. We are in a wagon train, some distance away from the base of that mountain. You shoot a reading to the top of the mountain, and that is 27 degrees. You move forward 1,000 feet. You shoot another reading to the top of that mountain, and that's 35 degrees. How tall is the mountain? This is actually a very, very real-life problem that the settlers probably encountered. I don't know if they knew trig, but when they were heading west and they saw Pikes Peak, they wanted to know two things. How tall Pikes Peak was, because they knew they were going to have to cross it, but just as importantly, how far away it was. In other words, what's this horizontal distance also? So there's a couple of things to solve for here. We'll call that x, the distance from there to there. And this is a right angle. Now, the solution here involves coming up with two trig functions and two unknowns, and solving a simultaneous set of trig functions. I'd be surprised if you didn't get something this level of degree of difficulty. Let's just go through how we would do this. What is the tangent of 27 degrees equal to?
Y over x.
What's another tangent function that I can write? What's the tangent of 35 degrees equal to?
Y over x minus 1,000.
There are your two equations and two unknowns, which almost always can be solved. In other words, remember the tangent of 27 is just a number. Tangent of 35 is just a number. So if I substitute the appropriate number in here, I'm going to be able to solve this by substitution. In other words, let's go ahead and multiply. Let's take the left side of the equation, multiply both sides by x. Okay. So now I have y fully defined. So over here, in place of y, I'm going to write x tan of 27. Now I have one equation and one variable. And do you have any questions about how to solve that algebraically? It's a little bit difficult, but what I basically had was two equations and two unknowns, and I used substitution to solve for, to put it into one equation and one unknown. So to solve this, I'm going to multiply both sides by x minus 1,000. So now I have tan of 35 degrees times x minus tan of 35 degrees times 1,000 all equals to tan of 27 degrees times x. I write it that way just to illustrate that these are numbers, so that's just a coefficient of x. So now I can bring the right side over to the left. I have tan of 35 degree x minus tan of 27 degree x. Move this to the right, and I have 1,000 times tan of 35 degrees. Factor out the x, leaving tan of 35 minus tan of 27. And it's all equal to this number here. Divide both sides by that. X is going to be that quantity. That's a number. That will give you the distance from the mountain, from the original spot. And then once you solve for x, solving for y is relatively easy. Just substitute whatever you got for x into this equation on the left here. That gives you the height of the mountain. It's pretty clever, isn't it? I mean, if you think about it, the fact that you can be 100 miles from that mountain, and in fact that's when you spot Pikes Peak. When you're traveling from the east to Denver, you spot Pikes Peak when you get about 100 miles from Denver. So 100 miles from Denver, they were actually able, and as all they had to do was go some distance in, 1,000 feet, take another reading, and they can tell how far they are from the mountain and how high it is. I've just always thought this problem is just too clever, that you can actually figure that information out from just taking a couple of readings and measuring the distance that you move. Yeah. Now, all of that might be affected a little bit like by the curvature of the Earth. If you're dealing in feet, the curvature of the Earth doesn't usually cause any inaccuracies, but if you're dealing in 100 miles, it might. So the fact that this bottom line actually has a slight curvature on it from the curvature of the Earth might affect things. In fact, I'm sure that it does and would have to be taken into account if it was significant. And 100 miles might be, I don't know. But typically you don't. Certainly not at this level trig. You don't take into account the curvature of the Earth. All right. That's the only kind of problem like that I can think of. There's going to be numerous problems of this type where you end up with two equations and two unknowns. And you have to solve that system of equations. But as long as you can come up with two equations and two unknowns, you're always going to be able to solve it.
He's given us things like this, but I can normally just go to law of science to solve that.
Okay, law of sines is a little bit...
Yeah, so you have another way of going around it.
It really only needs to be used on non-right triangles. I can't emphasize that enough. And most of these problems that deal with mountains or poles or flags or buildings, they're all right triangles. None of those are not right triangles. So usually when they give you real-life problems that involve something, casting a shadow or something, you're dealing with a real-life triangle. Now, if they give you ships that leave a port, and one sails to there and one sails to here, how far apart are they? Then you got to solve that triangle, which is not a right triangle. Then you're going to be using law of sines and stuff. Here, I'll give you a little quiz. You start out using the law of sines or the law of cosines to solve this triangle?
I guess the law of cosine, but
Yeah.
I don't know what the law of cosine is.
Have you, I don't know, is that something you want to cover?
Yeah, why not? I've struggled with the past year, so.
Okay. We'll label the side opposite big A as little a. Label the side opposite big B as little b. And this is little c. So since we're trying to solve for a, it's a squared equals b squared plus c squared. It kind of starts out a little bit like the Pythagorean theorem. But then you got to subtract 2bc cosine of a. And there's 3 different laws of cosines. In other words, depending on which side you're trying to solve for. If I'm trying to solve for side c, then c squared equals a squared plus b squared minus 2ab cosine of c. Do you see the pattern?
Yeah.
So b squared would obviously be a squared plus c squared minus 2ac cosine of b. Okay. Well, here we're trying to solve for a. So we'll use this first equation. So a squared equals 8 squared plus 10 squared minus 2 times 8 times 10 times the cosine of 30 degrees. Everything on the right side of that equation is a number. So a is the square root of that number. Okay. Once we come up with a, let's say that it is 7. I don't want to take the time to go through all the math. To finish solving the triangle always requires the law of sines. You have to use the law of sines to solve any triangle that's not a right triangle. It's just that sometimes you start out using the law of cosines. You can't use the law of sines until you get at least one relationship between an angle and its opposite side. In other words, when I started out, I knew one angle was 30 degrees, but I didn't know its opposite side. So there's no way to use the law of sines to begin here. But I can use the law of cosines to solve for this side, and now I have this relationship. And the other, I really only need to solve for one other angle, and then I can calculate the third without using the law of sines. But wherever you have to use the law of cosines, you have to use the law of sines at least once. There is one other situation which you begin using the law of cosines, and that's this one, where you know all 3 sides. Okay? It's not intuitively obvious how we do it. We're going to solve for angle A. So, 7 squared equals 8 squared plus 10 squared minus 2 times 8 times 10 times the cosine of angle A. There's the only variable. That becomes a simple algebraic equation to solve for. At some point, at one point, you have to take the inverse cosine to come up with A.
All right.
Okay? In other words, let's just go through the math here, just in case it's not completely clear what we're going to do here. So we'd have 49 equals 164 minus 160 cosine of A. Subtract 164 from both sides. You get negative 75 equals minus 160 cosine of A. Divide both sides by minus 160. You get cosine of A equals 75 over 160. That's less than 1. This is a possible triangle. Take the inverse cosine at this point. In other words, whenever you're solving for an angle, it's going to require an inverse trig function. If I want to solve for A here, A is equal to the inverse trig function of this number, 75 over 160. That's just an angle. Once we solve for that angle, let's say it's 33 degrees. Now we finish the problem using the law of sines, because now we have that one relationship. We have an angle and we have its opposite side. So I can solve for angle B or angle C using the law of sines. Now, there would still be only one variable. In other words, if I want to solve for angle B, it would be the sine of B over 8 equals the sine of 33 degrees over 7. Again, there's only one variable right there. And again, in order to solve for B, we're going to have to take the inverse sine of this number right here. All right, I don't know if I got off track or not. We started talking about the law of sines and the law of cosines, and so I figured it was appropriate to solve a few triangles. I actually saw an interesting, go ahead.
That fraction that was 75 over 60, does that have to be less than 1 for the triangle to be possible?
It does. If you end up with this, it's not a possible triangle.
Okay.
Sines and cosines range is from -1 to 1. In other words, this is not possible. You can't have the cosine of any angle being equal to 1.1.
Could it equal?
Yeah. Cosine of 0 equals 1. I draw my cosine curve. There's 0 right there. And there's 1. So the cosine of 0 degrees is 1.
Okay.
So the inverse, in other words, if I said cosine of B is 1, well, B is 0 degrees. Same with secant and cosecant. If you are solving an equation and you get secant of theta equals 1/2, impossible. Secants and cosecants live in the greater than 1 and less than -1 territory.
Okay.
In other words, here's what secant looks like. And that's 1, and that's -1. So you'll never see a secant of an angle being in between 1 or -1. Secants of angles would be equal to maybe 2, or infinity, or a billion, but never 1/2, or never 1/4, or never 0.
Okay.
And that's one actual vital aspect in solving triangles, is knowing that, because lot of times they'll give you dimensions of a triangle and it won't actually be a working triangle. In other words, if I gave you this triangle, if I said this side is 5 and there's a 30-degree angle and this side here is 100, that is not going to be a possible triangle. If we go to use the law of sines to solve what I've just given you here, we'll get the sine of this angle is 2 or 1 point, is some number greater than 1, telling us that this is an impossible triangle. And that's how you tell if it's an impossible triangle. I mean, it's clear that when I made it 100, it's impossible, but what about 11? Is that a possible triangle? Well, the only way I really know how to know is to use the law of sines to try to solve it and see if we can come up with an angle that fits right there. It's going to have to be pretty small because the smallest side of a triangle has to be opposite the smallest angle. And we've already got 11 opposite a pretty small angle of 30. So this is probably a possible triangle, but I wouldn't really know until I went to solve it.
Okay.
Have you studied the case of the ambiguous triangle, or the ambiguous case of the law of sines? Or is that something you're even doing now? That may have been something you did a couple months ago and you don't really need to review. But it's the only difficult part of the law of sines, is figuring out how to handle that ambiguous triangle problem.
I've never heard of the ambiguous or anything like that. So.
Well, let me just give you an example here. If I said, in other words, if I didn't draw the picture of the triangle, and they don't usually, what they usually do is they'll say angle A equals 30 degrees, side C equals 10, side A equals 8. They'll give you those 3 pieces of information, and they'll say solve the triangle. Well, it's called the ambiguous case because in this particular instance, there's 2 different triangles that fit this description. There's the other one. Notice everything is the same. That's still 30, that's 10, that's 8. In other words, all 3 pieces of information are the same for both of these triangles. So if they start out by giving you that information, you need to be able to come up with both triangles, not just the one on the left. And there's a nifty little trick for doing it that doesn't involve you really memorizing much. It just involves trying to solve this and allowing for the supplementary angle for C. Unless you have any other specific problems, I'll continue on this and I'll show you what I mean here. I don't want to waste the last 10 minutes if you have other stuff that we have to cover.
Let me just take a quick look and see if there's anything in here that...
Okay.
Here's one that... Okay, so does the bearing of the line of sight to the east end of the Royal Gorge footprint form a point 325 feet of the west end of the footbridge across the Royal Gorge is 117 degrees.
Having a hard time picturing what you're describing here. All right, let me draw the bridge. So there's the bridge going over the gorge. We have a river flowing down here, flowing in that direction. Well, actually I can't draw it. I'm looking at it from a side view here.
You have a picture here. I can try to describe that instead.
Okay.
So it looks like the length of the bridge is going to be. Okay, so first there's a horizontal line that's going to be 325 feet, and on the right end of that is the bridge that just goes straight up. Yeah, like that. And the angle on the outside of the hypotenuse. If the 325 line kept on going and then there was that angle with the hypotenuse on the outside there, that's 117 degrees. Yeah.
Okay.
And it wants us to find the length of the bridge.
The length of the bridge. This distance?
Yeah.
Okay. What's this angle right here?
So it'll be 180 minus 170.
117?
17.
There's one thing that trig and geometry is a worthwhile skill to have. It's subtracting numbers from 180. Almost all of geometry involves you constantly having to subtract numbers from 180. So it's a pretty good skill to get, so you don't have to use a calculator. Now the problem is easy, right? What equation can I write?
So that would be tangent 63 equals y over 325.
Y equals 325 times the tangent, 63.
Yeah.
This must be, when you say a bridge, that must be like the pillars that hold the bridge up, right? In other words, you have a bridge that has...
Well, it's actually like that hypotenuse is actually like looking at the river.
Oh, okay, okay, I got you. So so this is a bridge that you would walk in this direction on.
Yeah.
Oh, okay. All right. I was picturing it completely different, but...
Yeah, the wording's really confusing on that one. Glad the picture was there.
Yeah, really. Yeah, once you draw the picture, once you can make a picture on any of those word problems, then it always comes down to solving a triangle and using these trig functions. Again, these are always right angle problems, and so I don't need to use the law of sines. All right.
Oh, forgot to ask, did you ever get that checked?
I'm pretty sure I did. Yeah, I'm sure I did. In fact, let's see, I think I'm looking at it right here. Hold on. Yeah, $108, yeah. Thank you.
So
I appreciate it.
At this point then?
I've got an invoice that I haven't kept up current. I've got a couple weeks to get caught current, but I've got a record of all my sessions and my scheduler here. And so I don't know precisely what your balance is, but I can certainly send an invoice to you as soon as I come up with it. Can't be too much because you paid, I think you paid for like a week in advance. You might have paid through last week, but maybe through the week before. So there might be like 2 sessions of it. I'll certainly look and send an invoice. Should I send it to you, or let me hold up. Sure, I have your email address here. Professor Grumps, that's you?
Yeah.
It's a cool name. Where'd you get that? Just
I used to call my cat Professor Grumper Kent because he's really grumpy.
Ah, okay. It's funny, when I first saw this, I started thinking, is that some teacher that's wanting to test my tutoring ability or something? When I first saw your first appointment, I didn't know what to think. So. All right, Daniel. Well, I will talk to you next Tuesday at 7:30. All right? Have a good one. Bye-bye.